our pleasure to welcome our colleague, Rute Pedro, a member of our local Atlas group. So she got her PhD in 2017 from the University of Lisbon within the Atlas collaboration, working at the time on Higgs analysis and TileCal detector. So since then, she continued to work on TileCal activities as a corresponding associate at CERN, and in 2019 was nominated coordinator of the TileCal calibration. She also started to explore machine learning techniques as a postdoc at our Big Data Competence Center, and more recently, she started an R&D collaboration with the Institute for Polymers and Composites at the University of Minho to develop novel plastic scintillator materials for future calorimeters. So today's seminar is going to be about the activities related to TileCal. So Rute, whenever you want, if you can, please share your slides.
Okay, thank you, Liliana, for the very complete introduction. Let me then share the slides.
So 50 minutes, okay, and afterwards we'll have around 15 minutes for questions. Thank you, Rute.
Okay, so thanks also for inviting me for the seminar. I'll be talking about the tile calorimeter and how the performance and the construction of the system is bridging currently to the efforts that are ongoing on the design of future detectors. So the tile calorimeter is the central hadronic calorimeter of Atlas. It has a central role also on the experiment because it measures hadrons, jets, hadronic decays of tau leptons, missing transverse energy, and also assists in immune reconstruction and electron identification. Also participates in the trigger system, providing input to the level 1 calorimeter trigger. So it took 20 years since we've got the first, let's say, complete proposal for the Atlas experiment with the Atlas letter of intent being published in 1992 until we had the detector ready for operation. So we are now currently on the LHC project with the detector behaving well and taking a lot of interesting data for analysis. We will be facing afterwards the high luminosity upgrade of the LHC project. So that means another 15 years of operation. But as we operate the detector now, and we are on the experiment now, we are also 20 years away from the expected future project related with the future circular collider, expected to begin around 2040. So this project is it's a large accelerator, circular accelerator with about 100 kilometers ring, where the LHC will be an injector ring to this accelerator. So this means that we have 20 years also to start. Well, to design the experiments that will instrument this experiment, and I think it's a nice time to review a little bit what are the aspects that we dealt in the past related to the detector construction. So the outline on this talk will cover a bit on that. So mostly focus on TileCal, of course. So I will be talking about the design features of this detector, the LEAP contributions also. Then I'll focus on the detector operation now during the LHC experiments and its performance, and how we will prepare the detector to face the high luminosity LHC challenges. And also have a view on the TileCal in terms of lessons that we can learn to the future detector design, and also present you a little bit of the R&D plans that we have for the future, to participate on the future detector design and construction. So first thing first, let me start by the detector design features and the contributions of LIP to its construction. So the tile calorimeter is located right after the electromagnetic calorimeter. So this is TileCal here. It is structured in a barrel and two extended barrels. This system was designed to attain jet energy resolution that has follows this function here. So with a constant term of 3%, which is attained for very high energy jets. So it is made with steel plates as the absorber material, interleaved with plastic scintillated tiles, which are the active medium that emit scintillation light when crossed by the particles that come out of the LHC collisions. So the sampling period of the detector is about 18 millimeters, and the detector is constructed with with 64 wedged models that are arranged radially around the detector. Important for our current plan on research or of new scintillators, I would like to highlight that the plastic scintillators that TileCal employs are made of polystyrene doped with two wavelength shifting fluors. So the tiles, the scintillating tiles are read out by wavelength shifting optical fibers, which shift the wavelength of the emitted light by the scintillators to match it to the best sensitivity region of photodetectors, which are photomultipliers in the case of TileCal. We have several fibers bundled together and read by a single photomultiplier, and this basically defines the unit readout, the unit cell readout of the TileCal. So with this arrangement, we radially segment the detector in 3 layers, A, B, B, C, and D. Also we segment in pseudo rapidity with a granularity of about 0.1 in the long barrel and 0.2 in the D layers. So with this we have about 5,000 cells, and the fact that we employ a double PMT readout that makes a redundant readout of the cell from the two edges means that we have about 10,000 readout channels. Then about the signal readout and reconstruction, the PMT signals are shaped, amplified, and digitized every 25 nanoseconds. And we reconstruct the signal amplitude and time from 7 signal samples that are taken from the signal. And the amplitude is just a linear combination of the reconstructed amplitude for each of these samples. The energy is taken from the signal amplitudes. First, we converted the ADC counts to charge with the conversion factor, and then charge to energy with the factor that was determined with the test beam studies of the detector that were made pre-installation in the Atlas cavern. And then we have a few calibration factors which allow us to make the response of the detector stable over time. So for that, we have dedicated calibration systems which probe the detector response at different points of the readout chain. So a cesium radioactive source calibrates the optical components, the PMTs, and electronics. Then we have a laser light system to calibrate the response of the PMTs and electronics readout. A charge injection, which is responsible for determining the conversion factor of ADC counts to charge. And then also we can do an integrated readout of physics events. And we find out that this is very useful to monitor the full detector response as well. So we expect and observe that the cell response fluctuates in time due to the PMT and the scintillators performance variation, which we also have been observed to be correlated with the LHC operation. So the TileCal, let me just highlight two calibration systems which are a bit more complex. So one is the cesium source, and the other is the laser. So for the cesium system, we use three radioactive cesium sources that scan the calorimeter cells through the holes that they have. The sources are driven by an hydraulic system and move at about 35 centimeters per second, which gives us enough resolution to be sensitive to each unique tile in the detector. But also, so this velocity means that it takes about a few hours to perform a scan. So this is a system that we cannot employ very often. And then for that reason, the laser calibration system is important because it allows us to calibrate more often. So the system is composed of a laser light source, which is located out of the detector on a cavern. It's about 100 meters away from the detector. So this system also has some attenuation filters in a wheel that we use to adjust light intensity. And then we have a beam expander that guides also the light to 400 fibers, which in turn will dispatch the light through these 100 meters that we need to travel to put the light into the detector. And eventually we have a single fiber lightening each PMT in the detector. So we, so that the system was upgraded during the long shutdown one, and Lipes had an important contribution to development and construction of this laser system. We had more contributions to the TileCal construction, and here are highlighted all LIP responsibilities. So we mainly contributed to optics, to the optics instrumentation, but also to the electronics with PMT procurement and in the laser system. So it's much better to show all of this to you in pictures. Unfortunately, I couldn't find a picture of the contribution from Coimbra to the laser system, and well, I'll apologize for that. start with our contribution to the procurement of the scintillator materials. We also had an R&D project on scintillator production in collaboration with the Institute for Polymers and Composites of the University of Minho about 20 years ago. Which was very successful and in fact provided an important backup solution for the production of all the scintillators for TileCal that turned out not to be used or to be necessary. We also studied and optimized the scintillator fiber coupling at LOMAC. And optimize the uniformity of the scintillator. Here you can see the preparation of fiber bundles that were polished and mirrored at LEAP, all the 600,000 fibers that TileCal employs. Here's the polishing of the fiber bundles. And here the system for magnetron sputtering of aluminum coats in one end of the fibers. Finally, the quality control of the fibers, including the measurement of the reflection achieved by the aluminum coat. So you can see here a bundle which is polished on one side and here mirrored on the other end. We also developed and constructed a robot for automatic insertion of the fibers in the mechanical profiles on the detector. This is work done in collaboration with the IST robotics. And we participated also with the quality control of a subset of the PMTs used in the detector with a dedicated test bench. So it took 15 years since the first R&D started to construct the TileCal to get it ready for the first collisions. So you can see a nice summary plot slide here with all these the different phases that were involved in this. So R&D, construction, then the optical instrumentation with the fibers being put on the modules, electronics development, the calibrations of the detector modules that were ready, then installation in the Atlas cavern, commissioning of the detector, and finally in 2009 we were ready for the first collisions of the LHC. So now let me talk about how the detector is behaving on the experiments and also how we are preparing it to face the challenges that the high luminosity LHC will bring. So during run 2, we have made cesium calibrations about 2 to 3 times a year. This is a little bit less than what have been ideal, but in run 2 we had a problem with this system, and basically we had a suspicion that there could have been a leakage from the hydraulic system into the other parts of the Atlas detector. So for that reason, we could only use it when the LHC was off, and hence very few data points with this system to calibrate the detector. In any case, well, it worked, and we did calibrate the detector during run 2 with this about 2-3 times a year, which is good. So what we observe with this system and we calibrate for is the loss of response or the response fluctuations of the entire detector, and you can see here how the response is drifting as a function of time in run 2. Basically, we observed that the inner layer array is losing more response with the detector operation. This is comprehensible since this is the most exposed region of the detector to radiation. And we calibrate for it. With the laser system, we can calibrate in between laser cesium scans to basically correct for the PMT response variation in between the cesium scans. So these are scans that are taken very, very often, once a week. And the calibration factors are also applied to the energy reconstruction of the cells once a week typically. So we can see here the average PMT drift as seen with this laser data. And again, we see a larger fluctuation, downwards fluctuation for the PMTs reading the A layer, where the highest energy deposits take place. And an interesting feature that we observe is the loss of response of the PMT when we have the LHC on, and then the recovery of the response of the PMTs when we have these luminosity plateaus where the LHC is not colliding particles. So here is the average PMT response variation observed in 2018 for average per cell type. So basically you can see that the most affected PMTs are the ones reading the layers closest to the collision points, and the outer cells PMTs are being far less affected. So charge injection system is to calibrate the response of the analog amplifiers and to determine the conversion factor between ADC counts and charge. This is the distribution of these factors for the TileCal channels. As you can see from this plot, these factors are very, very stable with time, of about 0.03% stability, which is really stable. And time calibration is also a very important aspect of the correct energy reconstruction, because this means to measure and to adjust the digitizer sampling clock to the peak of the signal. And if we do not do this correctly, we can severely underestimate the energy measurement with respect to a well-timed readout of the signal. So this is also a very important aspect of the TileCal calibration. Then we also need to perform the noise measurements. Noise has two sources: electronics noise and pileup. The electronics noise is about 20 MeV for all the cells. This is measured regularly in dedicated runs without any signal in the detector. And then the pileup noise, by its very own nature, is dependent of the average number of interactions per bunch crossing, which is, you can see here on this plot. And this again is more relevant for the cells which are more closer to the beam pipe, experiencing the larger particle fluences. And we can also see from this plot that we have a good modeling of this dependency by Monte Carlo. Then very important as well is the detector operation and the monitoring of the data, the quality of data that we are acquiring with the detector. So for the operation, we have a dedicated detector control system to control and monitor the TileCal operation and the detector parameters. This is a system that is fully developed and maintained by LEAP. Then we have a run coordination team, maintenance team, and a data quality team that ensure the smooth operation of the detector. They continuously monitor and the data to identify and mask channels that are problematic. So here on this plot, you can see the evolution of the masked channels and cells as a function of time. So during run 2, we were below 2% of masked channels. And due to the redundant readout of cells, this translated into less than 1% of masked cells, which is quite nice. And also interesting to observe from this plot is that these dashed red regions where maintenance campaigns took place. So in these campaigns, they fixed all the issues that were encountered on the detector and fully recovered the system to be ready in the beginning of each year collision period. So overall, TileCal had an impressive 99.7% data quality efficiency in run 2. Now, moving on to performance, we use the response to isolated particles, hadrons and muons, to get a handle on how the detector is performing. So the ratio of the calorimeter energy response to isolated charge hadrons to the momentum, which is measured by the tracking system, which is the quantity that you can see on this distribution, is very useful to evaluate uniformity and linearity of TileCal. So also the response to cosmic muons is used to study the electromagnetic scale and the intercalibration of cells. So you can see here very flat cell response to muons as a function of the track of the muon. So this is probing different cells of the detector. And we see a good energy response uniformity also over the pseudo rapidity. The jet energy resolution is, of course, one of the most important parameters or metrics to evaluate the performance of the calorimeter. Of course, the jet measurement combines information from the hadronic calorimeter, TileCal in the case of central jets, but also of the electromagnetic calorimeter. But of course, TileCal is a very important contribution by measuring about 30% of the jet energy. So this is the jet energy resolution as a function of the jet transverse momentum achieved with the Atlas experiment. And we see that this functional form is compatible with the TileCal design goal for the jet energy resolution. So we are asymptotically approaching this constant term of 3% for very high magenta jets. So now let me talk a little bit on the high luminosity LHC challenges, which are related with the luminosity increase and the severe pile-up environment. So the detector is being upgraded in the electronics and also with a new high voltage remote system where LEAP is being responsible for. And also an important point is that in the beginning of the LHC project, the detectors were designed for a 10-year operation. And this high luminosity upgrade was not foreseen at the time. So the detectors will be pushed to limits, and we need, for the case of TileCal, to understand the detector aging, and also the radiation damage is very critical to this type of detectors with scintillators. So this must be studied, and also the implications that these issues have on the expected performance at the high luminosity phase. So the high voltage upgrade is a full responsibility of LEAP, of the Atlas team at LEAP. The regulation of the high voltage will be moved away from the detector to ease the access and maintenance, and also to avoid radiation. So this means developing new crate control and monitoring, and also finding cables that are needed to bring to the HV to the detector. We have several boards being designed in collaboration with LEAP's electronics lab. And for the cables, we have a partnership, let's say, with the Portuguese industry, or we are employing, let's say, Portuguese industry. So here's a photo of the crate, which is at the moment being tested. Now to optics robustness. So as I said, we need to study the radiation hardness of the TileCal optics. This is very important because the bulk active elements cannot be upgraded. This would mean rebuild the entire detector, so we cannot touch them. We know that the radiation degrades the scintillator light output and also the transparency of the wavelength shifting fibers. Here on this plot, we can see the total ionization dose as a function of the longitudinal coordinates, and for different regions in radial regions of the detector. As expected, this region here corresponds to the innermost A layers, is more affected to radiation. So this is the area where we should put our concerns more. To study the optics response, we compare the detector response to cesium, which is the entire detector, and the response to the laser, which is the PMT fluctuation only. So comparing the two, we can see, for instance, in 2017, that this particularly irradiated cell lost about 3% of light output. So we measure this quantity, the relative light output, and accumulate it over the years in run 2. And we plot it against the simulated dose. In total, for this, the very same cell that I showed here, we observe about 9% of light output decrease. So we do it for all the detector cells, and we observe, for instance, almost no degradation on the D layer and the B and C layer, but up to 10% on the innermost and more exposed cells. Then we try to model this degradation with the dose. Typically, the light output decreases exponentially with it. So we are fitting an exponential function with the goal of extrapolating to future runs. Looking at these plots where we see the dose we still have to face until the end of the high luminosity LHC at about 4,000 inverse femtobarns, and the point where we are, we can immediately see that this is a large extrapolation because we are only on the beginning of the curve. So it's a bit difficult to make precise scenarios for that time for the moment. But we did extrapolate to the end of the run 3, which in fact will be the detector scenario for the beginning of the high luminosity, which is the run 4, right? So what we observe here with this extrapolation is that we are expecting more or less the same degradation in run 3 on the optical elements that we had on run 1. On run 2. So let's say it's doubling the degradation, so about 20% for the worst case cells. Yeah, and still the B and the C and the D layers doing very well by then. So what's next on this work? And this is the PhD work plan for Beatriz, who also has already been working on the optics robustness study with the run 2 data, which was her master thesis. So what's next is analyze run 3 once we have it, because more data will help constrain the degradation model to do more precise extrapolations and so on. Also, it will be very important to investigate those rate effects because CMS observed a very large, observed larger degradation of the scintillators for lower dose rates in their hadronic calorimeter in the end cap. Although the scintillators have a different material, but this was a severe effect that they found out to be happening. So we started this work already, and our preliminary results agree. And this is something that can be motivating because it can play in our favor. So these dose rate effects can play in our favor because at the high luminosity LHC we'll be facing dose rates which will be about 7 times higher than we have now. So the degradation rate can be lower than. Another important point is to study the effect of light loss on the detector performance at the high luminosity. So this means simulating a degraded TileCal response on GM4 and evaluate the impacts on the detector measurements. And for this, we are thinking about a few metrics. So the jet energy resolution, of course, is a flagship metric for calorimetry, but also it's the sensitivity to hadronic leakage is important. This is used for to perform electron identification because, as you can see from this plot, the ratio of the energy deposits on the first layers of the hadronic calorimeter is useful to distinguish between electrons and hadrons, which are background for the electron identification algorithms. So this is the PhD work plan of a new PhD student that we have welcomed in the Atlas Portuguese team, Rute Machado. Of course, we also need to think of mitigation strategies, and those exist. So one idea is to compensate the light output loss of the scintillators and fibers with higher efficiency photodetectors. And for that, we will be replacing the PMTs reading the A layer of the calorimeter in the phase 2 upgrade. Okay, so now the final moment of the seminar with the lessons that we can take from the operation of TileCal to the future detector design, and also the R&D plans that we have to participate on this active effort on the design of the future experiments. So some introductory slide about the requirements for calorimeters that the FCC electron-positron collider and then its later hadron collider version will pose. So the FCCE will have a center of mass collision energy that will range between 90 and 350 GeV. So this is something that can challenge the calorimeter design in some ways which are not yet quite identified. At least this is what came out from the discussion of the symposium on calorimetry organized by the ECFA Detector R&D roadmap. Then for the hadron collider, we'll have an impressive center of mass for the collisions of 100 TeV and luminosity that is about 30 times larger than the LHC design for the instantaneous luminosity. So these projects will require from the calorimeters excellent energy resolution, which is more important for the electron positron collider, where we'll be doing precision physics. And then the time resolution should be of the order of 20 picoseconds to fight pileup. So by referring pileup, this means that this requirement is more related to the hadron machine. Then we will need technology to stand a very challenging radiation environment. Especially for the hadronic collider case. And also calorimeters need to be read very fast to cope with data rates which are very large and never faced by any experiment before. So the open directions to respond to these requirements are a particle flow, where we combine calorimeter and track information to make to measure particles. Dual readout that performs an event-by-event compensation of the energy measurements by determining and measuring the electromagnetic fraction of the shower. High granularity segmentation is important, so we want to measure energy with a very good resolution, but also have a resolution on the position where the energy was deposited in the calorimeter, and a precise timing, as I said before. So it is important to, and TileCal bridges naturally to some of these projects, because a tile-like design is being proposed as a central calorimeter, hadronic calorimeter for the FCC hadron collider. This could also be a valid option for the electron positron positron collider, but I mean, this is something that is still to consider and to investigate. So this calorimeter employs steel LEDs and scintillating plastic tiles. So the difference here with respect to TileCal is the introduction of LED. Then the granularity is much finer, 4 times finer, both in azimuthal angle and in pseudo rapidity. We have again the individual readout of the tiles with wavelength shifting fibers, this time into silicon PMs, and also this time we have 1 silicon PM per fiber, so we can really read tile by tile and actually reach a much finer granularity in ETA than the detector is being designed for or simulated for. So other concepts are available besides this TileCal-like calorimeter. So for instance, the integrated readout of scintillators with CPM. So this means integrating also the front-end electronics into the active volume of the detector. A dual readout solutions. And also silicon-based high granular calorimeters. So there are still, of course, a lot of questions. And it's only just reasonable to ask ourselves what kind of input can the TileCal operation and its performance along the experiment history what input can it give to this effort? So one thing is for sure, the detector design must optimize the calorimeter response through the experiment lifetime. So this means the light yield and the detection efficiency. And we have a response which is very complicated in these complex systems that depends on a lot of the design factors. So scintillator properties, the sizes of the components, photodetector type, and so on. So you can think of the response of a given cell in the detector as a compound response of scintillators, fibers, photodetector, and each one of these elements in turn depends on intrinsic properties, such as in the case of the scintillators, the scintillation efficiency of the material, but also the transmission efficiency. Then for fibers, the efficiency of the coupling between the fiber and the tiles, the efficiency of the wavelength shifting phenomenon, then also the transmission efficiency, and the reflectivity efficiency in the one end that is mirrored. And also on the photodetector, we have the efficiency of the quantum efficiency to detect the light, and also the gain. So with natural aging and the history of this response with time changes, so natural aging implies that this efficiency have a time dependence, and radiation damage means that they depend also on the dose and on the dose rate. So it happens that on the TileCal, we have a unique data set to try to disentangle the contributions of these different effects to the overall response of the detector. Because as TileCal is constructed, we have access of a very different shapes of the components, lengths of fibers. We have material placed in several regions of a dose map that varies a lot with the detectors. That means we have access to very different total ionizing doses and also dose rates. And there is an additional advantage, is that these materials are suffering from aging and degradation due to radiation in situ conditions, which are impossible to reproduce in the laboratory, especially in what comes to the dose rate, which is very low on the experiment and almost impossible to reproduce in laboratory. So we thought that machine learning could teach us something when exploring this unique data sets, teach us something about the model of the response of the calorimeter, and of what, at least tell us what are the leading effects on this response. So an idea that we'll try to follow, and this is also work plan of Beatriz, is to do a combined fit of the TileCal geometry parameters, so giving as input to the machine learning model the different cells and geometric characteristics of it. And so entrain a DNN regression model to learn the optics response that we have measured already, but then we want to the model to reproduce. Yes. So with this, the idea is to investigate the dependence of the model that we obtain, the machine learning model, on the different detector parameters and the different dose conditions. So we'll be looking to things like what is the dependence of the degradation on the dose rate, or what is the most impacting factor on the degradation of the calorimeter. Is it the tile, or is it the fiber? So this is, for instance, this last question is important to decide between an integrated readout with a silicon PM directly on the tile, or readout through wavelength shifting fibers. So finally, and hopefully I still have time, to introduce you this new project on R&D on brighter and radiation harder scintillators. So this is important because regardless of geometry optimization and the technology choices that we'll have, the active material must improve to maximize initial light yields, to provide more radiation hardness and more detectable light. That means the best possible matching between the emitted light wavelength and the photodetector efficiency peak. So novel materials look promising, PEN and PET, and I will not try to say these names. So these polymers have interesting scintillation properties. One is that they scintillate without the addition of dopants. Remember that in the case of TileCal, we have a polystyrene base with two wavelength shifters, which have to be carefully tuned, and, you know, the concentrations and so on, to make out of it a good scintillator. So this is an advantage. Then the emission spectrum that they have already is well matched to the typical photodetector efficiency. So you can see here the emission spectrum of PEN in black, PET in blue, and this scintillator, commercial scintillator that is used here for reference in red. So you can see that PEN is already very close to what a commercial scintillator is yielding. Then PEN has larger light yield than this expensive commercial scintillator. This you can see here on this table. It has about 10,500 photons per MeV, to be compared to 10,000 emitted by the Bicron scintillator. Then another aspect which can be interesting for other experiments is that PEN has large radio purity and good mechanical properties. So it has been proposed as an active Wittig structure in low background experiments, such as direct dark matter searches or neutrino observatories. Then also, PEN affords a good, an energy resolution of about 10% at 1 MeV, which is better than Bicron. Considering the radiation hardness, there have been irradiation studies of PET and PEN sheets bought directly from Goodfellow. So with the cesium gamma source, they irradiated these sheets up to 10 and 100 kilogray in 67 hours. So you see here the dose rates that we can test in laboratory are much higher than the ones that we have in real life on the experiment. So what we can see from their results is that PEN degrades less. So this is the percentage damage after irradiation. So PEN degrades less for both points of those that were tested, and PET degrades more, but then here we see the permanent damage. That means letting the scintillators rest after irradiation to see how much they recovered. And we see that PET recovers slower. It takes 22 days to recover to the maximum value. But interestingly, it shows a larger recovery than PEN, especially for those rates and doses which are closer to the real detector in situ conditions. So they have, let's say, complementary, or they have properties which can complement themselves in a positive way to what we want. So we reinitiated the collaboration that we had 20 years ago with the Institute for Composites and Polymers of the University of Minho. This was an original initiative of Professor Amélia Maio. And the goal of the project is to develop and investigate samples of PET, PEN and PEN blends. So to see whether PET and PEN blend in a synergistic way, and if that is the case, what is the best material formula? So what's the best proportion? And also we'd like to see whether is it advantageous or not to add dopants. So we will characterize the scintillators samples at LOMAC. Also, we wish to optimize and set up a scalable manufacturing technique to do so, and then characterize the radiation resistance of the best samples. So I leave you here with a photo of an equipment that they have at Minho. So this is an extrusion machine, and I will not even try to explain what the components of this machine is. I can identify here, you know, the point where you feed the material in, which usually is polymer granulate that you put inside, and then it's blended, and I mean, it will go out of the machine somewhere. But okay, we trust our colleagues. they know their job. So to summarize, I will not tire you with many details. I just wanted to leave you with some punchlines. So we have in-house an expertise and experience gained from our contribution to the TileCal construction. The detector is now operating and performing very well. The phase 2 upgrade projects are ongoing, and we have a direct participation to them. We are studying the expected detector performance at the High Luminosity LHC. So at the same time, we identified this radiation hardness as the critical aspect of the plastic scintillator-based calorimetry. For that reason, we are investing in R&D on potential radiation harder scintillators. So this is a new project at LIP. And well, hopefully the ongoing discussion on the ECFA roadmap for the R&D on future detectors will help us lighting the way, and perhaps open new opportunities for contributions and projects. So thank you.
Thank you, Rute, for this very nice talk, very complete.